All right, folks. Well, welcome back. Hopefully, you're able to watch the video yesterday. I didn't, and kind of pick up what we were talking about. Again, I haven't seen many of you. Actually, I haven't seen anyone lately, and so please come by and get your questions answered if you have any. I know this material is not that difficult, but I think for those of you who've had physics already, it is pretty straightforward. I'm more worried about those folks who have not had physics yet and are still kind of new to this. That yes, I think this material is pretty straightforward, but I've taught it forever, and for those who've had physics, this is something you learned last semester, so we all take it for granted. But for those of you who are new to this, then make sure you come by and you see me and get that extra help. Okay, I apologize for the delay in getting the practice to you. I've had issues with trying to get the material together and also make sure that it's material that you can legally have. And so I'm going to try to finalize the practice for the first part of the discussion of the unit here where we talked about interpreting position time graphs. I'll try to have that up to you by this afternoon, and that way you can practice that. And then I'm in the process of working out and finishing the packet for you to work on these velocity time graphs here and interpreting them and getting practice and doing some basic calculations involving slopes and accelerations there, so that we can start the kinematics equations today. And that's my hope, that we can go ahead and get that done. Okay. All right. So real quick, let's go ahead and let's pick up with where we left off with yesterday. And I want to go ahead and read and redo this for you. I know that yesterday was kind of all scrunched up in there, so it was a bit messy. So I want to go ahead and I want to work this out for you again really quickly to give you an opportunity to see if you have any questions on it. Okay. All right, so the basic idea is that you need to, first of all, be able to interpret this velocity time graph. The velocity is plotted along the y here and time along the x here, and be able to trace then the motion of this object. And this, remember, this graph traced the motion of a baseball player as he was going out and catching a fly ball. Okay, so the object then is moving in one direction. Okay, so let's go ahead and let's draw what we have here. So this is our baseball player here. Okay, so there's our baseball player, okay, of mass m, starting out at the time. And let's go ahead and extend out our table here, our graph here. So this is time is going to be equal to 0 seconds. So this is the start. So this is at the start here. Now, if you notice with the graph here at the start, then the velocity, his velocity is at v0, 0 meters per second. We can obtain that from the graph here because the graph here starts out at 0. Okay, so that's his starting point. We don't know where he starts out at. Remember, for a velocity time graph, we don't know anything about position, but we do know that at the very start of this, he is at rest. So he's at a standstill. He's at a stop. Okay, so he is stopped. He's not moving. Okay. Then what do we notice? He starts to move. He starts to move. Okay. And then, so let's plot what happens here at point A. Which is 1 second into the motion. Okay. So t now is t1 is going to be equal to 1 second. Okay, at 1 second into the motion, we see then, plotting straight over, that he has a velocity at v1 of 2 meters per second. Okay, all right. So with that said, then let's continue on and let's see what happens. Then he continues on at the next second. Okay, so let's go ahead and plot this here. Okay, at t2, which is 2 seconds into the motion. Okay, so at t2, we go ahead and, using the graph again, we plot. So this is just review of what we've done so far, folks. So we trace up from 2 seconds, get to the point on the curve, and then trace over to the y-axis, and we see then that at velocity at 2 seconds, his velocity is 4 meters per second. Okay. And then continuing on then at each 1 second time interval. Okay. Okay. At t is equal to 3 seconds. So at 3 seconds here, same thing. We trace up our line, up to the graph. Okay, the graph right here, and we notice then, and then trace over the y-axis, and then we notice then that t is equal to 3 seconds. Okay. We notice then that his velocity at 3 seconds is 4 meters per second. So we're basically just drawing this from what we have here. Okay, so that gets us to point B here. So we'll talk about that in just a moment. Okay, At point C, and then let's go ahead and then take a look at the last second here that we are measuring his movement here. Okay. At T is equal to 4 seconds. Okay. So we go ahead and we trace up from 4 seconds, and then we trace over, and then we see that at 4 seconds, he is moving, and V is equal to 4 seconds, he's moving at 2 meters per second. So we can see from the graph here that what his speeds are. We can determine that versus time, and then now we can see it in a linear manner here, how he's moving. Okay? All right. So if you notice here, it looks like we obviously see then that as he moves from 0 seconds to 2 seconds, he's speeding up, and he's changing the way he moves, and so therefore he has an acceleration. Okay, so we can calculate for the acceleration in this first time interval here. We should be able to determine the acceleration in the second interval here, because from the graph here, we notice then that since we have a positive slope, remember the slope from velocity time graph gives us the acceleration, and since he has a positive slope here, his acceleration is going to be positive. So he has a constant acceleration here, which we can solve for, and which we did. Okay, so I'll bring that up for you in just a moment. Okay? And then if we take a look at the time interval between, and if we notice then the acceleration for A1 and A2, the acceleration A1, whatever it is, has to be equal to the acceleration A2, because we have constant acceleration. Okay, so we have constant acceleration here, okay, constant non-zero acceleration, and then we get to the time interval between 2 seconds and 3 seconds, and we see that here that the acceleration, because the slope is 0, the acceleration here is 0 meters per second squared. Okay, why? Well, first of all, the slope is 0, but then we notice then here, if we take a look at this, okay, the velocity that we start out with here at that time interval and the velocity that we end up here at that time interval are exactly the same. So in this particular instance here, if we take a look at it, the velocities will be the same for the second and the third, between the time equals to 2 seconds, time equals to 3 seconds, the velocities are the same. Okay, so the velocities are the same because the acceleration is 0. So between those two, okay, time intervals, since the acceleration is 0, the velocities are the same. So in the first 2 seconds, the acceleration is the same. In the second and third second, the velocities are the same because the acceleration is 0. Okay. All right. And so with that said, then we take a look at the third. So that's going to be A3. Okay. And then we take a look at the third. Between the third and the fourth second, we notice then that the acceleration is going to be negative because the slope is negative. Okay, and so therefore then, if we take a look at this, we should notice then that the velocities should be different. Okay, and since we have a negative velocity, let's go ahead and finish up here with our analysis here. V final here, which means then V4 is going to be less than V3, which means then V final is going to be less than V initial, okay? Which means then we're going to have a negative acceleration, and that gives us our negative acceleration when we calculate for it. Okay, and we see that, folks. Okay, and so let's go ahead and take a look at this. So our calculation yesterday showed us all of that. Okay, and so we analyzed the calculation here. There was the acceleration between we have here between for the first 2 seconds here, we have the acceleration. We calculated all the way here. And we have then a positive acceleration with a positive velocity, positive slope. It means then that the object is speeding up. Okay? And so then we calculated for the acceleration between 2 seconds and 3 seconds here. Okay, V final and V initial are the same. Acceleration then is going to be 0. That means the object is maintaining a constant speed, not a constant acceleration. I mean, arguably you can say then that this is a constant acceleration as well, but the acceleration is 0. Okay, so so we can say then that in this first instance acceleration is constant. It is constant, but non-zero. Okay, we can say in the second one then acceleration is constant and is 0. Okay, And the last one you see then the acceleration, then as we look at the last one, acceleration here is negative. It's negative because V final is less than V initial. That means then the object's slowing down, not because it's simply because it's negative. It's slowing down because the slope is negative. If we have this slope here, if we have the actual graph here, we see that the slope is going to be negative, and that's how we know it's going to be slowing down. However, if we didn't have the graph and we had this negative acceleration here, we would compare it to the velocities here, which are both positive, and since acceleration and velocity are both opposite direction, that's how we know then that this particular acceleration represents the object slowing down. However, the slope is constant, so therefore this is still, acceleration is constant. It is constant, but just like the first one, but non-zero, okay? Okay, so when we have constant acceleration that's non-zero, the velocity always changes. We have a change in velocity. When the acceleration is constant and zero, the velocity does not change. Okay, so here in this case then, and let's go ahead and write this out, okay, delta V then is not zero, which means then we have always changing. Here, delta V then is going to be zero. Okay, the change is going to be zero. And same thing down here. And let's go ahead and indicate that. Okay, and in the last instance, then delta V will not be is also not zero. Okay. All right, so that's everything that we did yesterday, and that kind of sums up for us then how we're supposed to approach using graphs to obtain information about the movement of the particle. Okay, also obtain information about how the particle is moving. So we should be able to translate this graph here into this motion diagram here. So that you should be able to do, but we should also be able to take this graph here and the information obtained from this graph and do all this work down here as well. Both the picture and what we've described down here essentially gives the same type of information, but you should be able to do that. And so looking at what we've done here, the graph then is rich with information, and you have to be able to obtain, be able to understand what the graphs mean and to be able to interpret the graphs, because graphs are a very, very useful tool in science and in any math. Okay? Graph allows us to make sense of the numbers. It gives us some idea of how the numbers and the data is related to one another. And then from that, we should be able to find patterns, hopefully, if any exist, find patterns that we can use to make predictions with. Okay, so that's why you need to make sure you can interpret these graphs here. Okay, all right, well do, folks. Let's go ahead then, and let me go ahead and let's take a look at the problem here. I want you to take about a couple minutes to work out this problem here, and then we'll go over together. Okay, and what I'd like you to do then is drawing the picture here. Let's go ahead and practice drawing that picture. Well, this picture will be pretty straightforward, but let me go ahead then and ask you to work on this problem here. Draw the picture and then calculate then describe the car's velocity, this toy car's velocity, and calculate for its acceleration, its average acceleration. Okay, so go ahead and get that done. Okay. All right, let's go ahead then and let's take a look at what we have here. Okay, so we have then, and let's take a look at what we have here. First of all, I think the answer to the first part of the question is pretty straightforward. I think we can see that here, okay, from what we're given. Okay, so when this car's velocity, again, if we take a look at this, then if we notice in the car's velocity, it's slowing down because it starts out here. Remember, this is a velocity time graph. So velocity along the y, time along the x as time proceeds here. And if you notice here, let me point out something to you. Time here is not at 0 seconds. We actually start timing this at 10 seconds. Or make sure you understand this. This graph here only gives you the time interval between 10 and 16 seconds, which means then we could have been recording, we could have recorded this toy car's velocity before 10 seconds. It's just not given to you in this graph. So you got to make sure you read the units on the graph and read the information on the graph carefully, because you've noticed here we are not given 0 seconds. All the graphs we've done so far, we started out with 0, but this one, and make sure you understand the graphs do not have to start at 0. Okay? And so make sure you understand then that the window of time that we're looking at here actually starts at 10 seconds. And again, we could have been recording the motion of this car at 0 seconds. Okay, but here you're only given information about the car's movement between 10 and 16 seconds. And so, if you notice here, could you find the car's motion at 10 seconds? Well, you can't, based on the data, based on this line here. But remember what I told you is that you can extrapolate backward. Okay, so you're actually only given the time from the line here. You're only given the time, velocity from 11 seconds. And so it's up to you then to trace the line back. So let's go ahead and let's take a look at this. And I'm going to do this for you. Okay, so how do you extrapolate? Well, you take the line and you extrapolate it backwards. Okay, so backwards here, roughly about right there. Okay, right there. Okay, and so and so let me go ahead and straighten that out a little bit. Okay, so there we have it. What we've done here is we've extrapolated the line backwards. We've moved this line backwards. Okay, so again, the actual data point themselves. Okay, so let's go ahead and let me make sure you understand this. Okay, this is an actual data point that we've collected. Each one of these diamonds here represents a point that someone has actually recorded the movement of this toy car. Okay, and so the very first data, the velocity is recorded at 11 seconds. The second one is at 12 seconds. The third one at 13 seconds, and the fourth one at 14 seconds. The last one at 15 seconds. Okay. All right. So with that said, then the question that you need to that we want to ask then is, what was the car's motion at 10 seconds? Well, it doesn't fall within this data set here. The data set only has 1, 2, 3, 4, 5 data points, which means then whoever did this experiment only recorded the velocity of the car at 5 different time intervals. However, the car was already in motion. How do we know that the car was in motion? Because, folks, here, if you take a look at this, at 11 seconds, the car was already moving. It had a velocity already, and that means that before 11 seconds, it already had a velocity. And so how do we find that out? We find that out by what we call extrapolating. Okay, we extrapolate, which means then we take the graph and we move it backwards, or we extend it. Okay, and so when we extend this this graph backwards, and this is what we can do with graphs, okay, which we cannot do with just numbers. We can predict then what the velocity then was at 10 seconds. Okay, so let's go ahead and let's take a look at that really quickly then. Okay, at t is equal to 10 seconds, which we don't have. Remember, the data set here doesn't have, but we can extrapolate backwards. At t is equal to 10 seconds, it looks like the speed of the car then, at t is equal to 10 seconds, the velocity here, if we extend it back here, is about, the velocity of the car then is about 0.13 meters per second. 0.13 meters per second, and we obtain that through extrapolation. Let's do the same thing. Okay, so they stopped recording at 15 seconds, but can you tell me then, and again, at 15 seconds, the car is still moving, okay? Could we determine then what is the speed of the car at 16 seconds? Well, of course. So let's go ahead and extrapolate again. That means we extend this line down to about 16 seconds, and I'm going to say it's about right there. Okay, so we've extended the line down to 16 seconds. Okay? And so what we're going to do now then is let's go ahead then, and at this point here, what's the graph does not give us, make sure you understand, the graph doesn't give us this. So can we find then the velocity at t is equal to 16 seconds? Okay, again, the data points don't give us this. We can, because by extrapolating, okay, what we see then here is this. Okay, we see then if we take at 16 seconds here, let's go ahead and do this at 16 seconds, and then we trace it back to the y-axis. At t is equal to 16 seconds, the velocity then is roughly 0.06 meters per second. Okay. What we have just done is what we call extrapolating from a graph, extrapolating data from a graph and using that information to make predictions about what information that we can obtain without that information being given to us. And again, this is the power of graphing, folks. Okay? All right, so with that said then, now we've included actually a couple more data points here, folks. So we have 5 here, but we have now 2 more. So we have a total of 7 data points that we can use to describe the motion of this car. Okay, so let's go ahead and let's do that really quickly. Okay, so we have a car here. So we have a car, and let's write it out here. Okay, so we have a car. There's our toy car of mass m. Okay, we start moving here. Okay, All right, so time here now, the time here now is not 0 seconds. We start out actually T1 is 10 seconds. Okay. All right, and so let's go ahead then, and they want us to find the acceleration. Okay, and so let's go ahead and I'm sorry, at time is equal to I'm sorry, 10 seconds. We said then that the velocity by extrapolation, we saw then the velocity was 0.13 meters per second. Okay, and then 1 second later, and I'm sorry, I'm running out of time here. So at 1 second later, let me go ahead and finish this up here. At 1 second later, which is t is equal to 11 seconds. Okay. And so remember, this data point is not on here. That we obtained, this one we obtained through extrapolation, and this one also we obtained through extrapolation. Since now we have, let's go ahead and use it. Okay, so at t is equal to 11 seconds, okay, which represents the second velocity. Then at 11 seconds here, let's go ahead and take a look at this. The velocity is roughly, let's see, at 11 seconds. Let's go ahead and draw the lines up here. Velocity then is roughly what, 0.15 meters per second. Okay. All right, and then let's go ahead and continue on here. Okay, and then we go to the next second. So now this is t is equal to 12 seconds, which is going to represent the third velocity here. Okay, so t is equal to when t is equal to 12 seconds, the velocity here is what, 0.109. Let's just call it that. So 0.1, not 0.11. So it's going to be about well, let's go ahead and do it. Let's just call it about 0.11. Okay, so 0.11 meters per second. Okay, all right. So what I would like you to do then, to finish up here, and since I'm out of time, what I would like you to do is finish up this diagram here. Okay, so we've labeled then the first 3 seconds with this data point here representing the first one, which was extrapolated data. And then we had the second and the third points here represented by the actual data points we're given here. I want you to plot out the remaining 4 data points there and show me how it looks. Plot out the remaining 4 data points, show me how that looks, okay, on your paper. And then what we'll do is we'll continue this tomorrow, and then we'll answer the question then, what is the average acceleration? And hopefully when you did calculate for it, and when we do calculate for it, you will get an average acceleration that will be the same for every point in time during this motion here, because we have constant non-zero acceleration. Furthermore, let me ask you this: since if you notice here, this represents a negative slope, which means then that we will have a negative acceleration. Okay? Does this indicate by itself? Does it indicate by itself that the car is slowing down? Well, we obviously know that the car is slowing down. The toy car is slowing down because of the velocity changes from a high velocity to a low velocity here. But in terms of the signs of the acceleration and the sign of the velocities here, how do we know that the car is slowing down? Okay? So make sure you get that done for tomorrow and submit that. Make sure you get that done for today's lecture, okay, and submit it. And then what we'll do tomorrow is we'll pick up with this graph and this finish drawing this picture here. Okay. All right. Very good, folks. I will see you tomorrow.